All right. Welcome, everybody, to the March 2021 CJUG meetup. Tonight, we have Amazon Corretto, Journey to Latency Reduction, presented by Yashai and Kelvin from AWS. So what is CJUG? We are the Seattle Java user group. We're a thriving community. We talk about Java, the JVM ecosystem, and things related. There's mentorship and career opportunities. We have a lot of folks who have gotten jobs through people they've met through the user group. If this is your first time, welcome. If it's second time or beyond, welcome back. And next time you come, bring a friend. If anybody wants to help and volunteer, or if you'd like to speak, feel free to reach out to any of the CJUG organizers. Johnny and myself are present. Otherwise, you can email us at leadership@CJUG, and that will go to all the organizers. We are a growing community. These stats are already out of date. We're past 2,100 members already. We are looking to have virtual meetings for the rest of 2021. Upcoming events, the Fuji.io is hosting a series of tours. They're friends of OpenJDK. It's a great place for information about OpenJDK. And they have an ongoing event kind of tour. So feel free to look into that. We can post the link in chat. So logistics, the bathrooms, food and drink are in your home. Use them as you need. Tonight, let's see, we have Yashai and Kelvin. They're from AWS. So they'll be talking tonight about Corretto. Our sponsors are JFrog, who, through their generous contributions, have allowed us to host these meetups, and AWS for providing speakers. So with that, I'll turn it over to Yashai and Kelvin.
Thank you.
There we go. Hello, everyone. Welcome. It's my pleasure to speak at the Seattle JUG. I used to visit when it was close by, but since the pandemic, we're all cooped up at home. Thanks, Jonathan, for reaching out, and Freddie for doing that in the past. And we finally here. My name is Yashai. I've been at Amazon for almost 5 years now, leading the Amazon Corretto project from the beginning. I'm part of the AWS Developer Tools organization, where we build additional services like in my team, for example, the AWS Code Artifact service, the Code Commit service, and adjacent to that, Code Build, AWS SDK, CloudFormation, Amplify, and anything developer needs to build on AWS. And with me is Kelvin. I'll let Kelvin introduce himself.
Thank you. I've been here at Amazon just a little over 1 year. I started with Java back in 1996 with a real-time Java, and worked in that area for about 20 years, spent about 4 years at IBM, and now I'm very happy to be at Amazon working on making Corretto more timely and performant.
So with that, I'll jump straight into our agenda. So what is this Corretto thing, and why did we build it? And then I'll talk a little bit about Java 11. It's kind of weird today, where we just released a couple hours ago, 3 hours ago, Corretto 16 or Java 16. Still, the current long-term supported version is Java 11, and still, unfortunately, a lot of services still run on Java 8 and older. And I want to talk a little bit about why 11 is still very interesting and why do you want to do something about it. If you're more brave and want to go further to 15 or 16 as of today, there's a lot of goodness coming in there along similar veins of what JDK 11 does in terms of performance. You just have to keep up. We'll talk about that in detail. And then we'll jump into AWS Lambda, the Lambda service that lets you run functions as a service, and see how Corretto and Lambda play together. And Kelvin will take us through Shenandoah, and we'll tell you a little bit why does LBS care about Shenandoah and what are we doing there. So with that, I joined Amazon the beginning of 2017, but starting late 2016, internal Amazon teams needed to start supporting themselves. At the time, Amazon was running on pre-built versions of Java, particularly I think from Oracle. And what they've noticed that without a Java team at a company this big with so many different services and so many different types of software built on the same JDK, it was incredibly hard to keep the version of Java up to date. And as you know, every quarter we release a new version of OpenJDK with security patches. And if you're running anything in production, you want to be secure. At Amazon, security is our first and above everything else thing we deal with. And we just couldn't move fast enough. So a new release would come out, but it would come with some surprises like a crash in C3, or we found a corrupt zip stream when using Apache Tomcat. Now, for somebody running 1 to maybe 50 services, that might not even hit you, and you might not even see that scenario. But in Amazon, when you run tens of thousands of services and you release a JDK across all of them, we almost always find something every quarter that broke. So our goal was, how do we move to a place where we can actually take the latest work that the community has built and put it into production as soon as possible? Eventually, once we got there, we said, well, can we optimize performance? Can we get more speed, as in lower latency, or more throughput out of our servers? Can we utilize the memory better? Can we have better observability, as in less outages, less running out of memory? And over time, we kept growing and expanding our team as we found new opportunities. So what enabled it? So we went after, we took OpenJDK and started building it. And while it seems trivial, you can go to the repo and build it. There are gaps between that and actually deploying something in production, and especially in these years. So the first thing was that we were able to fix a few compatibility issues. They're very small, but they're enough to break a significant amount of our services. And then we used, all of Amazon runs on CI/CD pipelines, which means even if we release something that has a bug, it's very typically caught either in build or integration tests, but even if not, it might roll into a very small fraction of production, and we'll catch it there and roll it back and then have a time to go back and fix it. Still, teams were asking us, what is this Corretto thing? We've been using Java forever. What is this new thing you're bringing to us? And we had a lot of this explanation to do of, this is really OpenJDK. Java is, or Hotspot is OpenJDK. You just used something from a different vendor that packaged it slightly differently. But by working with us, we can give you GC improvements. We can provide performance benefits. We can backport things from newer versions of Java without service team having to try and port to a new version. At the time, this was Java 9 that never actually became a long-term supported version. And we're able to bring a lot of improvements over. Over time, also start making our own homemade bug fixes and improvements. Slowly, we showed success with a few teams. We earned their trust. We started expanding. And in 2018, we basically were able to run across all the company. So it took us about a year from starting in earnest to build a team to deploying this across all of Amazon. But in 2018, customers running Java on AWS started reaching out to us, sometimes directly to me, sometimes through our partners. And they start saying, hey, we need a version of Java that we can continue running without paying for. We've been using Java 8 for a long time. We never had a bill associated with Java. We always had this multiple years of long-term support. And all of a sudden that was gone. And Amazon has this principle called customer obsession. And when customers ask us to do something and it makes sense, we go ahead and do it. And by the end of 2018, we took what we had internally used, mostly on Linux and some Windows and Mac for development, and turned it into a production release of a product called Corretto. So what is Corretto? It's a downstream distribution of OpenJDK. It does long-term support with no cost. And feature releases, as you can tell, I wrote this earlier than today, since the right feature release today is JDK 16. And it's a drop-in replacement. That meant customers are using whatever version of Hotspot can go and drop Corretto in and not worry about too much. It's not that everything is always 100% perfect. But in our experience, when we update a version, what we typically see is there are breakages, and they all have to do, or I would say, I've seen one case out of like 10,000 cases that this wasn't the case. Typically, they have to do with the fact that the team picking up a new version of Java haven't been updating for a few quarters, and have been hit by breaking changes coming from security changes or small behavioral changes that happen every quarter anyways. So in order to make that happen, customers told us that they want a single JDK to rule them all, as in they want one version of Java, one vendor of Java to deal with across all of their applications. And that made us work on multiple versions of Linux, on Windows, on Mac OS, on Docker, on x86. And when Amazon launched the Graviton processor, now Graviton 2, we also added support for ARM64, ARM32, and obviously the Corretto distribution is TCK certified, which makes certain that we're following the Java spec to the letter. By the way, if you have questions and want to interrupt me, feel free. If you think it's something very important, jump in, ask your question. If you don't think it's that critical, we have time at the end for Q&A. So support, we offer quarterly security patches at no cost to all users. We answer issues on Stack Overflow, on GitHub, or even Twitter. We actually had a customer one day come on Twitter and say, hey, I have a bug here, and we have a robot, picks it up, we went and fixed it. AWS premium support customers can file tickets, and they can have them processed in privacy, but we don't really care where you run. You can run it at home, you can run it on another cloud, you can run it on-prem. We will answer your questions and fix your bugs. All Java customers are our customers, is how we consider it, and how we treat it, and how we work. Because a customer might choose to work with AWS with some of his workloads, all of his workloads, it doesn't matter. They're going to get our support. And next comes a very important question. So, okay, Amazon, great job. You have your own release. What are you doing for the community? And we think this is a critical question. As we went on our path, we started the team as an open source team from day one. Our key goals are to sustain and help the Java ecosystem. Like I said, all Java customers are our customers. Even if they don't use Corretto, they are our customers. So if you're using any other distro, you will see patches from us in your distro. We will fix bugs. And the way we do it is, first, we're maintaining the long-term releases of Java 8 and Java 11 together with the community. In this case, we're talking about mostly Red Hat and SAP as the two main partners and this is bug fixes, backports, getting the builds ready, getting stuff out the door. For 8 and 11, where the work for 15, 16 is done mostly by Oracle. Then the next thing is the vulnerability group. So that is when security risks are being identified. They're shared among that group of companies plus a few more. And then we collaborate on getting bug fixes. The idea is security bug fixes. That means we don't want that, let's say one team discovered an issue. We don't want one version of Java from one vendor to have a security patch and others not to have it. So we all work together. We all get releases typically on the day. You'll see within the same 24 hours, all companies will get their Java releases out the door once what we call the embargo on these are lifted. They all happen on the same day. They all happen 4 times a year. Unless, in emergency cases, but I haven't seen too many of these. So that helps you know when you need to plan for your software upgrades, when you need to be ready. Next, we're a member of the JCP. We're contributing improvements on a regular basis to JDK 16 and on, beyond just supporting JDK 8 and 11. Kelvin is going to talk about some of these. We're spending a lot of effort on ARM64. We clearly have an interest in that. We have pretty interesting instance type in AWS. It's the C6G and M6Gs. They're very efficient, and we want to make them even more efficient by making Java work better on them. The ARM64 port started by Red Hat, and they did a really good job at getting us started. And together, both as a team and as a community, we keep investing in ARM64 optimizations. It's relatively new compared to the x86 port of Java. So there's still a lot of improvements to be had. And when I mentioned earlier JDK 15, JDK 11, this is where ARM really starts to shine. And as new versions come out, there's more and more improvements coming in them. Shenandoah, I'll just spend a minute on this, and Calvin will give you a whole spiel on Shenandoah. It's mostly concurrent garbage collector started by Red Hat that we're working on enhancing in multiple ways, and we'll go deeper into that and show you some examples. And latest, and really not that glamorous, just a lot of code reviews, a lot of helping the other community members get stuff in through the door. If you want to participate in open source, that's a really nice way to help others. You don't have to commit code. You don't have to invent something. You can just help people with reviewing and feedback and opening issues. There's one other thing Amazon is doing. I think it's important to note. We're all using Maven Central. Amazon is the sponsor behind Maven Central. We care deeply about both Java and open source, and picking up the tab for running Maven Central is, I think, essential for us as users of Java and for the community. So Java 8, Java 11, Java 15, I don't know if we can, is there a way to look on chat on how many people are using either version, but maybe keep it at the end for the Q&A. It's an interesting dilemma, and what I can see mostly so far is this is still Java 8, still a very, very large part of the Java workloads in production. Java 11 is getting momentum, and almost nobody's running Java 15. If anybody here has a different experience, I really would love to know, either later in the Q&A or talk to me. I know Jonathan has some different opinions on this. But I think we actually share the same opinion, but I'm talking about a little bit about how it works in reality. So let's look at this, the release cadence. Java 8 had support into early 2019, and then OpenJDK continues to provide no-cost support until right now, May 2026. And then we had Java 9 and Java 10, both had very short support terms. Java 11 came out, and again, we have with it support until 2027. And then all these feature releases come out. There's 1 month overlap between them, which means if you want to stay secure, you got to pick them up, and within that 1 month, you have to be able to upgrade. For some teams, it works fine. For some teams, it's not. And it's not just your code, right? It's the third-party code you're using. It's the Maven libraries. Was there a breaking change introduced in Java 16 that may break your Maven library? Hard to tell. It's a bet. What I can tell is at scale of tens of thousands of different applications, it's almost impossible to guarantee that most of them can move forward in time. So us as a team, as the internal kind of guardians of Java inside Amazon, are recommending for most teams to run on 11. And if you're agile and sure you can roll forward, we're seeing great results running on JDK 15. It is really valuable. I think one company also offers a medium-term support, so somewhere to here, and I think that's Azul. Our plan is support 11 until 17 comes out. It's not that far out, and then start moving somewhere around here to 17 when the rest of the ecosystem start adjusting. I think one thing of note that we noticed in Java 15 that was, I wouldn't call it surprising, was Java 15 no longer supports the CMS garbage collector. So if you're used to it and really know how to tune it, it's gone. It's gone. But what we found so far is the services that use CMS and thought they're really good at tuning it and they're running really, really great. By really minor tuning to G1, we got better results. So I wouldn't be afraid to go to 15, but only, if you're running a serious production service, you want to convince yourself, don't go to 15, 15 is done, go to 16, but really convince yourself that you're able to pick 17 within a month. And why am I harping on this? In Java 11, when it got released, we found at least 3 or 4 really critical bugs that impeded production that teams had to go and roll back to Java 8. Now, we all forgotten about them and they're all fixed. Some were fixed by our team, some were fixed by Oracle, some were fixed by Red Hat, but they're pretty serious. One had to do with TLS, one had to do with the G1 collector not really knowing how to collect effectively and making some mispredictions about when it wants to collect, things that will take your services down. So one of the things to worry about when a new version comes out, you want enough overlap and enough time to be able to test the application, stress test it on your own schedule before committing to moving on. Especially, if you're working in a company that runs some really big critical customer workloads, I'll definitely take that into consideration. If you're in the process of developing something new that won't launch for 6 more months, yeah, who cares? Pick 16 and move to 17 before you launch. Questions here? Okay, moving on. So what makes me excited about Java 11? There's, I know this is now history, a lot of new stuff, modularization, first LTS version with modularization, flight recorder, low overhead heap profiling. You can use var, you can go to war over var. That's what you choose to do. Bunch of new APIs in Java IO and so on. I'd say out of this list, the one thing I personally am really excited about is flight recorder. If you haven't used flight recorder, crack it open. It's very useful. It's a powerful tool. It will show you a lot of things you didn't know about your Java process. We've seen with Flight Recorder, the ability to debug complex service conditions trimmed down by 70, 80%. So if it would take us a month to figure out 4 or 5 problems at launch, we can now do it in 3 or 4 days. It's pretty impressive. Take a look at it. But the things that really made a huge difference, that is, if you don't even care about the code, you just upgrade from 8 to 11 and you want to go to production. You don't want to change anything. You're just like, my boss told me to go to 11. What is it that I get? The first thing is you'll find that if you never set garbage collector parameters, that you're now running G1 by default. And that might be surprising, and for some services that might create a change in behavior. Don't be afraid, G1 is great. It's even better in Java 11. The full GC is parallelized, so it's a lot faster if you ever hit it. Object copies improve, auto sizing of YoungGen is better, although that was the item where we've seen the bug. It's now fixed, it's all great. Overall, your latency is going to go down. The other thing is complex strings. Strings by default, since we're in America, I assume most of your strings are in Latin. And that means these strings by default will be about half the size. Just this change alone can reduce your heap size by 30%. That's pretty incredible. You're going to work really, really hard to get to achieve the same result, and you get it for free. And Kelvin asked me to remind you that Shenandoah is now available in Corretto 1109. If you're a Corretto customer on Java 11, you can use a pauseless GC. We'll talk about under what conditions it's useful, but it's a pretty big deal. If you want to use, for example, ZGC, you got to go to Java 14 and 15 before it's ready for production. Shenandoah is making regular backports into Corretto 11, and as far as I know, Red Hat is doing the same, but I'm not committing to that. So what are complex strings? So strings that are Latin 1 encoded, or in other words, think about them as simple ASCII strings, can now use a single byte representation instead of a double byte representation. That means that the heap size used by strings, roughly speaking, can be reduced by 50%. So let's take the example, Amazon, I don't know why it shows that, goes from 12 bytes to 6 bytes plus 1. Another cool thing, you just get it by default. There's nothing you need to do. It just works out of the box. Again, if your service have been running against available memory in the machine, you have to buy a bigger machine or rent a bigger cloud instance. This alone can save you a lot of money. It also means GC works a lot. It's easier for GC to work. You have less risk of just running out of memory and so on. I wanted to show a quick flag. If you're still on Java 8, there's this flag called, you have to use G1. You have to be on Java 8, at least U20. I hope you're there. It's a very, very old version of Java 8. So you can use -XX plus use string deduplication. So in one of our services, we tried it, and we found that about 80% of our strings have been duplicated. And it reduced our heap usage tremendously. The problem with that is because you're trying to, I'm not sure how the mechanism works exactly, but because the mechanism is when you allocate a string, it needs to see if the string already is there. It creates a synchronization point, and eventually what we've seen is while we're using less memory, the GC pause times are increasing to a point that we couldn't use it. But what it did is encourage us to experiment with JDK 11, because if we know, okay, we can't deduplicate a lot of the strings, but we can take about half the memory, why don't we go to JDK 11? So for teams here or engineers here that run on Java 8 and are not convinced Java 11 is a good choice, just go home, put this flag in, measure your memory. It'll give you a good excuse to think this through. It's also a very cool thing to keep in your back pocket. If you are running out of memory, you can't buy a bigger machine. It's too expensive. You don't care that deeply about pause times. I mean, it's pretty useful. Mainstream, probably not, but a good back pocket trick. So how would you do that? The way we did it is we turn it on, we capture the heap dump, and then we use this fantastic tool, the Eclipse Memory Analyzer, to find duplicates. I'm not going to demo and walk you through it, but I think you can take a note. There's a lot of good online tutorials. The one other thing you can do is what we've seen is our source of duplicate was one common library, internal library developed in Amazon, that kept recreating the string dollar something again and again and again and again. Like we had like 80,000 copies of the same string unnecessarily. So you can go back to the library and singleton that string. You don't have to generate it again, and you save some time without a whole lot of work. So let's talk about the migration. This is an example service. The specific service I'm talking about here is Lambda. So this is the AWS Lambda service that takes your request and routes it into the worker that's actually going to execute it. And I'll walk through the architecture here in a second. So the easiest thing was we had to do some dependency changes. So for example, JAXP or support for XML is no longer in Java 11. You have to go back to Maven Central and add that dependency. Done, easy. The second thing was we've been using one class from JavaFX. We never intended to. It wasn't very useful. It wasn't used in a lot of places, but it's one of these things when you have a non-modularized payload with a lot of APIs, somebody's going to pick one of them because they think it's a good idea. So that was another easy case. And we got rid of that. Other dependencies, we found that our log4j was out of date, our Mockito and byte bodies used for testing were out of date, and logbook was out of date. And all these 4 dependencies have to be updated because they all use very low-level APIs and private APIs that are no longer supported after Java 8. And again, not too bad. Go to your Maven or Gradle file, update the dependencies, you're good to go. Well, that's what we thought. But tests were pretty bad. So what happened is when we updated Mockito, we went from 1.1 to 2.25. We found a bunch of issues in, not so much in Mockito itself, but Mockito changed the contract on how to write tests. So while we keep patching the service regularly to deploy the latest security patches, and we're religiously following that, we were not very good at keeping our test dependencies up to date because, I mean, who cares, right? Well, it turned out that we should have been smart and spend more time on keeping our dependencies up to date. And I keep hearing people say, well, updating dependencies is not a developer's job. My job is to write code and innovate. And what I want to tell you is take all this free stuff that library developers are doing for you and invest in updating your dependencies. Java Update is one of them, but also test libraries. They're doing smart things. They're improving the libraries for you. And if you're a good team that writes a lot of tests, I'm not saying a lot is a good idea, but you cover most of your scenarios with tests. And then the test library introduce a break and change. You have a lot of test code to fix, and it's not always that trivial to fix the test code. So in this case, Mockito wouldn't let you mock with any string. You have to say now, I need to mock with a nullable string class. So that was semi-mechanical change you can do with a find and replace. But there are a little more interesting cases. Like in this case, We had an interface, and the interface definition says it throws an IO exception. And then we have an implementation that implements the interface. The implementation does not have to throw, right? It can just say return 0 in this case. But then whoever wrote the test case used the mocking on a certain implementation of the interface to see what the behavior would be. And then Mockito is now smart. It says, this implementation does not throw. You can't do that. Your test is invalid. This will never actually happen. And now, okay, not too hard. You can see the error. You can go fix it. But imagine that you have thousands and thousands of these tests across multiple classes, across multiple projects. Some of these are common libraries, and now you're looking at months of work to how do I fix up the test without being worried about breaking the code along the way, right? So learning from here is simple. Keep your code up to date, update your dependencies often, and you'll get performance benefits. And when the big changes come, they're not as daunting. With that, I want to jump to Shenandoah, and then we'll talk together. So what we did is we took Java 8 to Java 11, deployed it on Lambda, and then we took Shenandoah, made some improvements, which Calvin will talk about, and also deployed that on Lambda at a second stage. And then we'll talk about how we do these. How do you take this massive system like Lambda and deploy these also pretty big changes, and do it safely. So I'll quickly start. What's Shenandoah? It's a mostly concurrent garbage collector, which means for you in most cases, it will not show the characteristics of 100 millisecond, 500 millisecond pause times. Pause times are typically within 0 to 10, often a lot less milliseconds. It was started by Christine Flood from Red Hat, and currently run by Roman Kenki, Alexei Shipilev, and Jengir Gu. And so, like I said, the good pause times are not proportional to the size of the heaps. Java developers are conditioned to use as little memory as possible. So if we get a GC pause, it's not going to go into seconds and minutes. No longer the case. Huge deal. Second is the pauses are now constrained to a very small number. If you have a big service, you can easily have seen 500 millisecond, 1 second pause here and there. These are mostly gone with Shenandoah today and will be eventually eliminated in a couple of iterations. And Kelvin will talk about that. The gap is that there's a potential CPU overhead compared to parallel G1. We think up to 5%, but mostly we don't actually see it in production, but it is there. The bigger limitation today is that Shenandoah has a limited allocation rate, and it needs additional free space compared to G1 or parallel. If you miss it, you're going to start seeing what we call degenerated collections. So that beautiful number of 0 to 10 milliseconds is going to spike up to a few hundred milliseconds. And your mutator is going to throttle, which means the app is going to start slowing down before running out of memory. So Shenandoah is great right now at a limited, for a limited set of applications. It's not a generic solution for everything. However, when it works really, really well. And we will talk about tools we developed to help you estimate where is your app applicable or not. And we'll talk about what we're doing to make it a great default collector for Java. I think this is a good point to hand this off to Kelvin.
Sure.
Where he can go a lot deeper than me and a lot smarter than me about GC functionality and design.
So as we go, as we discuss this, because we will be going into a little more depth, if there are questions, maybe it's best to handle them when we're in the context. So feel free to raise your hand, interrupt me if there's something that I need to clarify. But some of the key features of Shenandoah are, first of all, it is regional, very much like G1. So the entire heap is divided up into regions, and we focus garbage collection efforts on a few regions at a time, or hundreds of regions out of thousands that comprise your heap. It does concurrent and parallel marking, concurrent and parallel compaction. Compaction is important because that allows us to allocate much more quickly. We can allocate from thread local allocation buffers with just a pointer bump. It also improves CPU utilization. It improves, I should say, cache behavior, and it avoids the reliability issues that come with memory fragmentation. So all of these are considered to be very desirable features of a time-critical, low latency garbage collector. One of the really important benefits that Amazon values is that it does support compressed OOPS. So as long as we're using less than a 32 gigabyte heap, we can use 32-bit pointers even on a 64-bit architecture, and that allows a more compact representation of your live data, typically a 30% savings or more, depending on the mix of pointers within your heap allocated objects. Shenandoah by itself allows us to get consistent latency below 10 milliseconds, but there have been some other causes of pauses with traditional JVM, but these are also being addressed concurrent with the improvements of Shenandoah. So concurrent weak reference processing, we would see long pauses with that, but now that's made concurrent. So your application can run concurrently with the weak reference processing. We don't see a long pause with that anymore. Similarly with class unloading, there's often, depending on how many threads you have, if you have thousands or tens of thousands of threads, you might see a long pause during root pointer scanning. And that is being made concurrent with JDK 17. The string deduplication effort, Shai was talking about how we got more compact representation of data if we used if we used string deduplication, but he saw the long pauses, and now we're making that concurrent also. So all of those causes of latency or pauses are disappearing as we move forward with Java. Next slide. To give an illustration of how Shenandoah is designed, Shenandoah consists of multiple phases of garbage collection, similar to G1 and parallel garbage collection. We do marking, then we do the compaction, which is described as evacuation. Then we do updating of references. That means anyone that's pointing to an object that was moved or evacuated has to have its pointers updated to the new locations of those objects. So those are three major phases of garbage collection, and those happen concurrently with the application. The application continues to run while those phases of garbage collection are occurring. Normally, with traditional garbage collection, you experience hundreds of milliseconds in each of those phases. Now we don't have those. What we have instead is these small coordination pauses. If you could hit the next, I think it just shows the animation here. We have these short little pauses at initialization of marking, finalization of marking, initialization of update refs, and finalization of update refs. Those pauses are typically under 10 milliseconds, and those are just coordination and start the effort, but not the complete effort of experiences pauses. And those are getting better. Let me just compare this really briefly with how G1 works. G1 is very similar to Shenandoah. It's regional. it does the marking concurrently. It has the pause at the beginning of concurrent marking. But then once it's done with the concurrent marking, G1 suspends all the threads while it does evacuation and updating of references. So that's where you'll see a long pause with G1. Now, G1 has a heuristic that tries to limit the length of that pause. So typical upper bound on the G1 pause time is about 100 milliseconds. And they limit how many regions they try to evacuate in order to keep that pause time less than 100 milliseconds. That's the general approach of G1. And it works very well most of the time. When we run G1, we see that rarely you will exceed what your target bound is on pause time, but it works most of the time very well. You go to the next slide, just to compare briefly with how parallel is it. Did we skip a slide? Maybe I lost a slide. This is one I wanted to show. With parallel GC, the marking also is a pause time. So with parallel GC, you put all your application threads to sleep, and you do the marking, evacuation, updating refs while everything's asleep. From a throughput perspective, this is very good because there's no coordination overhead between what the application is doing and what the garbage collector is doing. While the garbage collector is working, the application is asleep, so it doesn't have to worry about coordinating. So parallel GC offers the best throughput overall. G1 is slightly slower overall, slightly less throughput, but much lower latencies. The pauses are much shorter. And with Shenandoah, you go even further. You get a slightly greater overhead coordination penalty, but even lower latencies than with G1. Next slide. Okay, degenerated GCs. So this is what happens when Shenandoah is not properly provisioned. So if you ask Shenandoah to support a workload that is beyond its bandwidth capacity, you get something called a degenerated GC, and that basically stops the world and catches up. Let's go to the next slide, and we can begin to see some of this. We use two workloads to analyze this, and we use a lot of real-world workloads as well. And we have these synthetic workloads represented in the hypothesis test suites. These are out there on GitHub. HyperAlloc is one of the benchmarks. Extremum is the other. These both allocate high rates and keep a large amount of data live, and they churn through the live data in order to create a stress workload for the garbage collector. And this allows us to dive very deeply in our analysis of what's the good and the bad of different garbage collection approaches. So let's go to the next slide. When we run these benchmarks, we have two sources of information that we analyzed. One is we run the benchmarks with the GC logging enabled. So the GC logging tells us what's happening in each of the respective garbage collectors. The other thing we do, though, is especially the Extremum benchmark, it reports how long does it take to do certain important activities. It timestamps when the event was supposed to occur, and it measures when it actually occurred. And it reports that data so that we can combine that information about how long, what the latency is of the service request, and compare that with what we see in the GC logs and what we desire in terms of our maximum response latency according to what our service level agreement might be. If we look at the next slide, I think that's where we see the characterization of the workload that we ran. This was an Extremum analysis. We ran the workload for 10 minutes with a 768 megabyte heap. During this 10-minute time span, there were 3,763 collections performed. So that's a very frequent execution of garbage collector. In this case, this was a under provisioned configuration of the CPU. So we experienced 381 degenerated GCs. And if we look at the next slide, you'll see what this looks like in terms of the chart of response times. You'll see that for the first 160 seconds of this execution, there's a line that almost is indistinguishable from the y-axis. It's a solid straight line right at 0. That's the response time that we expect for this service. But as the service progressed, anything off of the 0 represents what we see as a degenerated garbage collection. Basically, every time we do a concurrent garbage collection, we are running a race between the garbage collector and the application thread. The garbage collector is running as fast as it can to reclaim the memory before the allocation pool is exhausted. Meanwhile, the application wants to chew up the memory, wants to keep allocating, wants to keep running at its full speed. And if the application exhausts the available free memory before the garbage collector has replenished it, that's when we have to do the degenerated garbage collection. The degenerated garbage collection puts all the application threads, all the service threads to sleep until it can finish the garbage collection. So you'll see at the start of this, it was able to do fewer degenerated garbage collections, and it was able to keep those degenerated garbage collections at about 40 milliseconds. So that's not a huge impact on your application thread. But things got progressively worse, and as throughout this application, we were experiencing garbage collection pauses of up to 37, I should say 370 milliseconds for a number of these pauses, and some closer to 150 milliseconds, 100 milliseconds. So this was clearly a situation where Shenandoah degraded in an undesirable, unfortunate way. And this is one of the weaknesses we've seen with Shenandoah, which is something we've been addressing with the development work that we've recently begun. Next slide.
I just want to mention one thing.
Sure.
This benchmark is for you to go and try. If you want to see how these collectors will work for you without having to change your application, you can look at your parameters, go to the page. There's actually a nice blog post that Kelvin just put up a few days ago that walks you through how to use it, how to visualize it, and you can estimate when you build new applications, say, which collector will work for me, what can I expect as a result?
Yeah, thanks. Do you want to talk about this, Shai, or should I continue?
No, you continue. Yeah, go ahead.
Okay, so one of the observations we've made is we've put Shenandoah on existing AWS services, is we discovered that sometimes these degenerate garbage collections would result not because the system was under provisioned, but because the Shenandoah garbage collector itself was making poor choices about when to do garbage collection. So remember, there's this race between the garbage collector and the service threads. Well, if we start the race too late, the garbage collector will almost always lose. So if we could start the garbage collection effort a little bit sooner, in cases where that's merited or necessary, we can avoid the need for degenerate garbage collection. I should briefly point out that the reason we don't always start the garbage collection at the moment we we have resources to do so is because we don't want to spend unnecessary efforts garbage collecting or too much efforts garbage collecting, because that would detract from our service capacity. So we want to do as little garbage collection as possible, but enough to always stay ahead of the application. So what I think, let's go to the next slide. I think that shows some of the so this was actually a real service, Lambda service within Amazon that we deployed with the Shenandoah garbage collector. And we experienced some problems because of the poor choice of the heuristic, and we improved them with some adjustments. I'm going to let Ishai talk about the Lambda service itself. He's much more aware of these details than I am.
Thanks, Calvin. So what I'll go through now is I'll talk a little bit about the Lambda service and then how we deployed these two improvements, JDK 11 and Shenandoah, and eventually the fix that made the degenerates go away, as I like to call it. And so Lambda is one of the biggest services, serving many billions of requests per day. It's an AWS service. It is a regionalized service, which means there's an individual stack of Lambda within each region, and then each of these shows up in multiple availability zones. That means availability zone means that there are actually multiple data centers distance further apart from one another to prevent, cases of fire, earthquake. If one data center goes down, the others continue to run, which is how you get high availability from these services. So in this case, a Lambda customer, as in that could be you, or could be me, you write a piece of code in Java or in Python, it doesn't matter for that case. You call invoke from your client, you send a payload, it reaches an application load balancer, which then finds a server called the front end. Unlike front ends in other places, this one doesn't run JavaScript and doesn't present any UI. It just takes your request and it authenticates it. It makes sure that you don't run your payload against a function that I wrote and you have no permission to run. It then goes and talks to another service called the worker manager. And the worker manager's job is to find you a worker. A worker is the actual EC2 instance or computer that will run your code for you. So yes, it's serverless, but at the end of the day, there are servers somewhere. We just manage them for you, right? So we find a worker, and then we send the payload to the worker. There's two modes. There's synchronous and asynchronous mode. Let's just focus on the synchronous mode for now. So the payload goes to the worker, and the worker crunches the data and then sends some data back to the front end, and the front end replies to you with say an HTTP response. 200, great, true, right? But in the meantime, this could have run for a long time. This request was open for a long time. So we have this interesting case of, and sorry, I forgot to mention, clearly this is written in Java. So as you might know, and if you don't, I think it's a good one to dive a little bit deeper into. When your code runs a mix of big and small memory allocations, long and short running, as in the memory is held for a long time and for a short time, this is where you start expecting to see GC surprises. And this service is not different. The unique thing about this service is because it's synchronous with your own code, that means every time your code sends, hey, compute this for me and tell me it was true or false, you're always tacking on tax of obviously the network and the load balancer, but also every millisecond spent in the service is directly added to the latency of your code. So obviously this is a place where we really, really want to work on the latency and take it down. So um, just this is a kind of a mention. We run out of in 24 regions. We run in 77 availability zones, and it's really hard to keep track because new ones keep coming up all the time. And the idea is that, okay, how do we go and deploy a fix? Like we just discussed, like we move to Lambda, move to JDK11 across such a vast amount of data centers, instances, and we make sure we don't break our customers. So what do? Some of this is going to sound pretty trivial. So we have a build stage. That's just your regular build machine. We have our own internal build system, but this looks like, in principle, like any build system you might use. We have test stages. So within build, we'll run unit tests, but after that, we'll have all kinds of, load tests and stress tests and integration tests and so on. And when this is all done and it's all automated, we hit our first region. How do we choose our region? We obviously don't go to the biggest AWS region with the most customers because, hey, we hate to break a lot of customers if we did something wrong. We also don't go to the smallest AWS region because are we going to get enough variety of use cases to make sure that we're really safe? So we pick somewhere in the middle and eventually go to bigger regions and then cover all the regions. So if I zoom in into one region, so the first region we start at has 3 stages again. We have the staging, the canary, and the production stages. And these are internal terminologies, and I'll expand on them for you to understand what each one means. So if I create a very simplified picture of what the service looks like, is we have a database. It's not actually, it's like a SQL database, but you can think about the place where we store the data. We have computers that get the new code called the staging computers. Then we have the fractional computers, and then we have the production. So we go from, say, 1 to a few to thousands as we progress with these. So the first thing we do is in the staging, we have a specific area in the database that we know is test customers. So if we, let's say, the new code created a problem and it, say, created a poison pill that destroyed customer data, nothing bad happens because it's test data, it's test customers, we can just zap it and roll back and continue. As soon as we did this, we start sending test traffic to the staging stages into production, and we make sure everything keeps working. Like, we didn't create extra load on the database. The responses that come back from the staging things, machines look fine. We're ready to proceed. And then we move to fractional deployment. At this point, we're not sending test traffic anymore. We're sending production traffic, but only a small part of it reaches the fractional, and then a big part of it reaches production. Now we're also starting to hit customer data, but we're feeling pretty safe because we run through all the tests and we run through the staging environment, and we make sure we're not touching customer. It's the production database, but we haven't touched real customer data. And again, we're looking, now we have more samples, more data, real customer data, real customer functions, and we observe. We look at metrics. And when I say look, I mean machines are looking at the metrics. There's no people looking at it. Something goes bad, we have an automated action to roll it back. After a certain amount of time, when everything looks good, the system automatically promotes from the fractional deployment to the full production deployment. And now, obviously exaggeration because we won't hit all the database exactly, but we have now access to all the database. So let's look at what happened. When we moved from Java 8 to Java 11, and people with sharp eyes will notice that I'm not actually telling you what the latency is, because that's data we don't publicize. But I think you can see the clear reduction in 4.9s, P4.9. So that's one request out of 10,000 was hitting up to the green line. But after we moved to Java 11, without any additional code changes, we got this really nice drop. And the drops are going to be different at different percentile. So at P50, this line will be a lot lower, and also the drop will be a lot lower. The improvement is lower. Percentage-wise, it's the same. Millisecond-wise, it's lower. As we go up, though, we start seeing effects. And now, after doing it with so many systems, I could say it's quite common. Up to 4.9s, we see a pretty steady and increased drop as we go up with percentiles. But once you hit 4.9s, you're going to start seeing secondary effects like downstream services, network issues, where you're not getting the same benefit. The benefits actually start dropping once you get to 4.9, beyond 4.9. So if we could get here, say, a 33% improvement, when we go to 5.9s, we'll get maybe 20. So then the next phases is we migrated to Shenandoah. And this is before we got to fix the heuristic. So this is still the thing that Calvin showed you earlier. And now we're seeing the same graphs, 2.9s improved again. So this is not 32% from the beginning. This is 32% from where we were with JDK 11. Basically, we had to go to JDK 11 to be on Shenandoah. 32% in 2.9s and 44% in 4.9s. And if you actually look at the graph, it's interesting, right? It doesn't look all that great. You can see the spikes with G1, right? But this line tells us where the 4.9s is. And then when we went to Shenandoah, you can see that the high 9, the 2.9s, for example, went significantly down, or the 4.9s went significantly down by 44%. But there's still these annoying spikes coming in. So, you know, if you look at the left side, it's pretty clear that the right side is better. But if you look at it, you still know there's room for improvement. Like, we would love these to disappear. So another engineer in the team has worked on trying to figure out when can we start the collection. There was some heuristic that was built into Shenandoah, but what we found out is it's starting too late. It's guessing a little bit too late on where to start. And this is when we picked up these benchmarks again. So we took hypothesis into two benchmarks and start trying to tune it so it runs just like Lambda. And now we can experiment with GC settings without risking our customers. It's really hard to, you know, to validate GC and operational parameters in production because you're afraid to impact your customers. It's also very hard to do it in test environments because you don't get exactly the same thing you get into production. So with hypothesis, we have a lot of knobs, and we can slowly tune it so the GC logs and the behavior start looking the same as the service. Now you can experiment. For us, it means experimenting with code and how to rewrite pieces of Shenandoah. But for you, it can mean experimenting safely with tuning of your GC. So, you know, what are the results after the move to Shenandoah? We didn't find any bugs. We had no customer impact. The early pilot deployments really helped us learn about the generated GC and its impact. We built a lot of confidence in our ability to run such a critical service with Shenandoah. It was already better than G1 GC, and we wanted more. So We rolled this out in November 2020. And this is a similar graph, not exactly the same graph, of what happened after we added the heuristics. So you can see all these annoying spikes. They don't completely disappear. We're not where we want to be yet with Shenandoah, but we're in a much, much, much better place than G1. So, but I'd say if you care deeply about latency, and you're within the parameters of Shenandoah, or by the way, it's not much different than ZGC. Although future-wise, we'll talk about what we're doing, which we think is super exciting. But currently, if you use the Z collector or Shenandoah, and you understand and you know how to measure the boundaries, you want to keep some safety margins, then you have a much better collector for latency available to you today for free in OpenJDK. For Z, I would say go to 16. For Shenandoah, you can stick with 11 and still be within long-term supported version and a pauseless collector. Again, so after adding heuristics, same thing. By the end of 2020, we launched it. It proved the theory. It was kind of nice to see how a developer is tinkering with a test system. That was only a few months ago, was just another engineer's dream, and be able to really move the world with that kind of fix. Customers enjoying even faster invokes now. And then Kelvin can talk about what we're doing next as the next big round of improvements.
I'm off mute now. So what we found is very lacking in Shenandoah, the way it's currently implemented, is support for generational garbage collection. And so we have actually begun a process of adding generational garbage collection to Shenandoah. This is an effort we're coordinating with the original Shenandoah developers with the Red Hat team. We've got a Java enhancement request has been published. It's under review by the community. And all of our code is out there now in GitHub, hosted by this Shenandoah repository of GitHub. We've completed 7 milestones of our own development. We have a lot of this working, and we're making very good progress in getting this demonstrated and into production quality. We actually hope to have some limited amount of experimentation and possibly even production before the end of this year. Next slide. So what you see here is this is simulation of the execution of a generational version of Shenandoah. What we've actually implemented is 2 instances of the Shenandoah garbage collector. We have one instance that's working on young generation, and that's shown in the bottom chart. That's a young generation garbage collector happening. It's actually triggered 4 times a second right now for this particular workload. And across the very top of this, you see the combination of how much memory is being used between the young gen and the old gen. And the middle line on this is the amount of memory that is being used by old gen. I should point out, I didn't realize this when I chose my my legend. That is not a zigzag on the old gen. What that is notice that it's a triangle for each data point. So that's pretty much a straight line, but it's a very slow growth in the old gen, and a very rapid recycling of the young gen. And the point I want to make is that the young gen is happening at a very high frequency and a very high priority. And that's in order to keep up with the very high allocation rate of this application. If you hit the next button, I think we'll see a summary of what this workload is. This is a 8 gigabyte per second allocation rate running at in a 30 gigabyte heap to support a 24.7 gigabytes of live memory. So that's actually an 82.3% utilization of heap memory with Shenandoah garbage collector, according to simulation. I should emphasize this is a simulation only. Our real world experience is not quite this high, but we expect to be much better than in the single gen. Let's hit the next slide, and I'll show you this exact same workload running on Shenandoah without the non-generational capabilities. So here we have to use a single heap to represent the same total live memory. And because we cannot distinguish our efforts between focusing on the young gen, which is very efficiently garbage collected, and the old gen, we have to do bigger garbage collections. They take longer, they consume more CPU time. And notice that hit the next and we'll see the summary here. We are using the same amount of CPU cores, the same allocation rate, the same live memory usage. We have to have a 55 gigabyte heap, which is only a 45% utilization. This is the primary benefit that we are addressing with the generational techniques. We're going to be able to run much higher memory utilizations than we can. Experimentally, we find that anytime we use over 30% of the heap with Shenandoah traditional at a high allocation rate, it begins to experience the degenerated garbage collections. The addition of a generational technique allows us to utilize much higher percent of the heap without experiencing degenerated garbage collections. Next slide, I think.
Is it true, Kelvin, to say that a good place to be with Shenandoah is not far above 2 gigabytes per second?
Yeah, especially with the single generational capabilities. 2 gigabytes per second is probably the where it's safe, where we've experienced success.
Yeah, so I think going back to hypothesis, that is a good place to find your sweet spot, because it is actually not one number. Like I said, 2 gigabyte is just a number. It's the mix of the object mix, the heap utilization, and the allocation rate. And if you go deeper, it's the mix of object size and the allocation rate has impact as well.
Yeah, and if you're willing to dedicate more cores to garbage collection, you can maybe push it in higher rates. But I'll turn this back to you. I think we're in wrap-up mode, Yishai. You want to?
Yeah, so first, I want to thank a lot of people that worked on this project. I mentioned some of them. We have Kelvin here. There's a lot more people helping with this project. I don't want to miss anybody. So you can go to Shenandoah page, look at contributors. I just want to help thank two other people beyond Kelvin who helped with these slides as well. Roman Kenke from Red Hat was polite and nice enough to fix all my mistakes in putting this together the first time. And Azim Jiva, who is our JVM team manager in the Corretto team, also spent a lot of time setting this set of slides up, which we plan to run for multiple jugs. And as we make more progress with deployments, and I'd say since Lambda, there have been several other teams that picked up Shenandoah with similar successes. This is not just a one trick pony or one, just one service that used it. We'll add more information and expand it. I saved a bunch of links to the end. If you want to learn about Corretto, if you want to learn about hypothesis, specifically want to know, this pull request has been merged already a long time ago. But if you want to learn about what was the code and the changes behind reactive heuristics, It's in that pull request for OpenJDK. It is the default heuristic now, so you don't need to do anything special to pick it up. The JEP for Generation Shenandoah, and the source code being actively developed. Of course, you're Java experts and want to look at it and help us with reviews and ideas and asks. OpenJDK is a great place, and Corretto is also a great place to find us. And with that, I'm going to leave time for questions.